On this occasion, we are going to present our research titled Approaching Design Flexibility to a Modular Deployable Bamboo Structure for Sustainable Architecture. It is an evaluative study through user participation experiment. I am Anastasia Maurina, working with my colleague Budi Anastas Prastatyama and my advisor, Dr. Vincent Bluing. We have been working on this project with support from an international NGO named Jubit International since 2016. In 4 years, we accomplished in applying our research into two real case studies. This is our first experimental project, a shelter for the Aquaponics Center we built in 2017. And this is the second project, a kindergarten that was built in 2019. The second case study collaborated with Arunika community. The keywords from our discussion today are bamboo, deployable structure, user participation, flexibility, and constructability. The most question come to us is why we are using bamboo. We believe that using local materials can promote sustainable development opposed to most typical construction materials. As we know, there are three pillars of sustainability. The first is environment, referred to bamboo availability and renewability. The second is economic, referred to as its affordability. And the last one is social, referred to as its acceptability. Bamboo is available in substantial and widespread in tropical areas, meaning that we can reduce our carbon footprint by providing building materials. And we can use bamboo from 4 to 7 years old, much faster than wood. Bamboo is also a low-cost material and can create financial gain opportunities, especially for communities in developing countries. Since bamboo construction is traditionally known, it is good to reuse bamboo to preserve traditional skills. But bamboo has the connotation of being a poor material. This image in society has changed gradually with the emergence of modern bamboo building design. One of the major issues in developing countries is to provide a good quality of building designs and construction to vulnerable people. For example, in Indonesia, we have a lot of disaster and we need to provide new buildings in mass and fast. Also, we have vulnerable communities living in remote areas or even in informal areas of the city. Bamboo, for all its benefits, is a valuable resource for solving these problems. In those contexts, we lack resources and expertise as well. It leads us to believe that prefabricated structural systems can maintain the quality of building structure. But we know prefabricated systems produce a uniform building in size and shape that doesn't fit the user needs and desire. It requires a prefabricated system that can provide design flexibility and also constructability. Design flexibility refers to a building's ability to comply with varying users and building functions and adapt to swift changes. In a nutshell, it can be configurable and reconfigurable in different sizes and shapes in the design and construction stages and user stages of the building cycle. Constructability or buildability is the extent to which building facilitates ease of construction in material preparation stages, design and construction stages, and reuse stages in terms of social factors, managerial factors, and technological factors. In this kind of situation, it is essential to involve the user as a decision makers in creating their identity and personal identification design that truly belongs to them. Users who participated in design and construction process were more satisfied. However, the next question is how the layperson can be a designer and a constructor in prefabricated design. Using modular deployable bamboo structure that can be compacted and expanded have a great potential to provide prefabricated design with design flexibility and rapid design and constructability.
We developed a deployable bamboo structure module, as you can see here, based on the mechanism of scissors-like element shown here. For each single module, there are several bamboo poles incorporated into the design and connected with several end-joint at several critical locations, and one adjustable bar that functions as an analog actuator. So basically, what the configuration enables us is to have several flexible options of multiple spans for a buildings that can be set up to have also second story from the get-go. We aim to evaluate the performance of this deployable module in terms of design flexibility and constructability in real-life situations. So whether it can perform to serve multiple functions in different locations, whether it can be constructed after it is moved to another or new site, and also whether it can accommodate the real needs of real users in real sites. We evaluate the performance of the modular deployable structure by examining two case studies from the experiments that we conducted between 2017 and 2019. The two case studies were located at two different sites in West Java, and they are supported by two different communities who become the users of the buildings that are produced from these modules. Throughout the experiments, we observed the performance of the design and the construction process that took place on each site.
The unit analysis of this research are design and construction processes and the physical artifacts. In data collection, several groups of peoples were given a design kit containing several structural modules. They configured the modules to become a building. Then, they also were given a construction kit to fabricate the modules. They moved the modules into the location and installed them according to the selected design. All processes and artifacts were analyzed descriptively to assess the flexibility and constructability based on multifunctional space and reusability. And to assess the constructability, we analyze the accessibility to labor, materials, and tools, construction methods and time, and then the modularity and size, and also the construction technology. In the next section, there will be two main parts. The first one is a description of SLE structural module in terms of architectural and structural performance. And the second part is an evaluation of the design and construction practice through two cases in the real situation with user participation approach. The significant invention of this structural module is the only one adjustable bar in each module for creating in a wide variety of shapes and spans varying between 3 and 7.3 meters. Some variation can also accommodate mezzanine floors. The structural performance was calculated by my colleague Alto Sagara for our previous publication. We used Gigantocloa apus with a diameter of around 80 millimeters and a wall thickness of approximately 10 millimeters. We get the safety factor for the compression limit is 2.5 and the tensile limit is 6. It is incredibly safe. However, the element bending will determine the limit of the structure.
The experiment was initiated in 2016 with the first prototype here test out the module's transportability and deployability. The same exact module was then moved to another location to serve a different purpose and different larger building span. As you can see here, it has significantly larger span compared to the first one. We developed this first prototype to basically see how the constructability aspect is on the deployable modules. We further developed the modules on the first case studies to further examine and evaluate the constructability aspect, this time with different users and different functions. And finally, with the second case study, we experimented on the multiple configuration capability of the modules by dismantling this one here and again move it to another location to serve another function, and this time with another different building layout. On all points of the experiments from 2016 to 2019, we incorporated various levels of users' participation. The first case study had community members participated in the development of building layout alternatives. We used scaled models of the deployable structure unit to introduce the system's capability, and later for the sixth group of participants to try and develop several different layouts by using a given number of modular units. They managed to produce 6 different configurations, from which only one would be chosen to be built into one-to-one scale pavilion. The chosen design was refined and finalized by the research team to fit the actual site, function, and budget. The construction process once again involved some community members who, although with some construction skills, were lacking the proper know-how of contemporary bamboo techniques. The modules were assembled on site, but the bamboo poles were cut to size at the different locations. This is because of the logistic constraints of the site. This picture shows the typical situations of a community meeting between community members and the advisory NGO partners, and also the research team throughout the entire process of building, design, and also the construction. In the second case study, the participants in the design process were not only the users, but also a number of architecture students. The introductions and the design workshop took the same format as the first case study, with the students divided into several groups to work on the same architectural program, and they were encouraged to produce multiple designs by using the same modular deployable structural units. And they managed also to come up with different layouts of the designs, which also further proves the multi-configuration capability of the modules. And again, as with the first case study, the chosen design to be built into real building were refined and finalized to meet the actual site size or condition, and also the updated actual architectural program, as well as the client's budget or the user's budget. One challenge was to configure the building enclosure relative to the structure, since the structural modules have their own formal limitations in terms of when it comes to the integration of the conventional building enclosure into with the structural modules. And so the team opted to separate the wall system entirely from the deployable modules. As you can see from the layout, these are the 6 modules, and this is the layout of the building enclosure. The video here illustrates the erection process and specifically highlights the duration that it took to erect the pre-assembled structural modules. We can see also the approximate number of people involved during the process, and that will become one point of evaluation also.
Observing the participant design results, we can see how the modules are organized in several linear organizations. Even they can make a curvilinear organization in case study number 2. The module also can be centrally organized and combined with linear, as we can see in the case study number 2. They can also apply the main advantage of this module, that it can be expanded in various sizes, resulting in the different building span and height. In case study number 2, even they can create a different shape resulting in different interior atmosphere. See the difference between the red area, blue area, and yellow area. When they finalize the design and use the space, we spot the difference between case study number 1 and number 2. The interior space in case study number 1 is formed between structural elements such as the SLE modules and mezzanine floor structures. While in the case study number 2, they divided the structural system and enclosure system to get much more flexible in space. The utilization of the height in case study number 1 is pretty interesting. The left side, the orange area, used the entire height of the building as one space, while in the right side, the yellow and green area, split vertically into two areas to accommodate more community activities. Regarding the reusability in case study number 2, 2 of 4 structural modules are used from the previous structural models. From the first prototype, moved to the temporary workshop and moved to the new building, as my colleagues mentioned before. It is proof that it can be reused in different settings. We conclude some points from the evaluation of design flexibility. First, the user could create variant building designs with variant organizations, variant configuration in size and shapes. From both case studies, we can learn two types of relationship between the structural and enclosure system in creating spatial flexibility. Last, the module can be dismantled and reused in different size and shape to accommodate the new building function. According to labor's accessibility, lay people were still assisted by students in process design and assisted by the trained worker in the construction process. One of the most important using bamboo as a material construction is preservation treatment. We have to make sure we can get treated bamboo locally in time because we have the problem in case study number 1. We have to transport it from the Middle Java. All bamboo modules can be cut by a handsaw, a chainsaw if it is available. Expert did all metal works at a metal shop. The design of joinery is one of the future challenges, so the layperson can replicate it easily. In the installation process, they use bamboo poles to push the point. In case number 1, the base have been anchored into the foundation, so they need fewer people to keep the module on the position. However, in the case study number 2, they need more people to keep it on the position because they didn't anchor the module to the foundation. One of the advantages of using these structural modules in terms of time is that they can simultaneously accomplish the design and fabrication process. Module fabrication, cutting, drilling, and assembly was lengthier than was predicted before. The most extended process was selecting bamboo to decide the position, especially the holes for bolts and nuts, because the holes should be as close as possible to the bamboo nodes. A module weighs approximately 30 kilograms and is 4.2 meters long. It can be carried by 2 people and then they place on the ankle truck to transport to the location. The installation process might take several hours depending on the numbers of available workers, and for the joinery, the adjustable bar is a customized part that a layperson cannot easily replicate. This SLE structural module can be fabricated easily because its modularity, built with light equipment and a less complicated construction methods. According to the construction time, it can be built quickly with more people. It means that it's more suitable in developing countries that have more people, than developed countries that have a high cost for human resources. The challenges that are the availability, the treatment bamboo, and metal joinery customization, especially for the adjustable bar. As a conclusion, the results show that modular deployable bamboo structure can be meaningful alternatives to traditional construction processes and can respond to rapid expansion needs of many communities. Last, we would say to thank you for all support, especially from Jubit International, Ms. Jung and Sin, Bamboo Nation Networks, Simanggung and Arunika Community, Graduate Student Government Clemson University, USA, and thank you for all collaborators in Sustainable Building Materials and Technology Research Group in Universitas Katolik Parahyangan Bandung, Indonesia. And thank you for listening. We welcome for any question and discussion. Don't hesitate to contact us through our email. Have a great day.